Hi everyone, this is our fourth and final lesson in our unit on waves. And in this lesson we're going to be focusing in specifically on light because light is weird. And therefore we're going to take a whole lesson just to unpack some of the weirdness of light and try to wrap our heads around it a little bit. Now, as a reminder, when we use this term light, we're not just talking about visible light, we're expanding out to include the entire electromagnetic spectrum. So that does include radio waves, microwaves, and infrared waves, as well as UV and X-rays and gamma rays. So all these different frequencies and wavelengths of electromagnetic radiation are all getting lumped in under this label of light. So those are the different types of light, but what exactly is light? It turns out that is a trickier question to answer than one might expect. All right. Now, so far, the way that we've been talking about light is to say that it's a wave, because this is our waves unit. So, of course, light must be a wave. And that's a good answer. Let's continue going with that for just a little bit. All right. So, one way that we can think about light is that it is this continuous, gradual, ongoing wave that is carrying energy along from one place to the other in these oscillating electromagnetic fields. And under this model, we have said that the brightness of light is a function of the amplitude of that wave, and then the color that we see within the visible range, or the type of radiation, whether it's a microwave versus an X-ray, is a function of the frequency of the wave. So then just to make sure that we still remember kind of what that all means. So if in the upper left here we see a picture of the wave that produces bright light, what might a dim light wave look like? So brightness and dimness, that's just a function of the amplitude, or in this case the height of the wave. So we're talking about a wave that is shorter, that doesn't go up and down, doesn't displace our particles vertically quite as much. All right. And then if this represents our red light wave, how would we modify this image to show a blue light wave? Color is a function of frequency. So with red light, we have a lower frequency, which means that our waves are more spread out, longer wavelength. Blue light is a higher frequency, which means that our waves are more squished inward and closer together. All right. So these are the basic ideas of our wave model of light. And there's a good amount of evidence to support that light is a wave. And so to understand this, we're going to think back to our last lesson about some of those unique interactions and behaviors of waves. And we see that light does a lot of these things, right? So light refracts. And as a reminder, refraction is that tendency of waves to bend as they transition from one medium to another, because the wave moves at a different speed in a different medium. All right. And so we see that with light, and that's where rainbows come from, that when sunlight comes to the earth, it includes waves of all these different frequencies, all these different wavelengths, which we then just perceive as white light. But when that sunlight hits the raindrops that are in the air after a storm, as the light moves from the air into the water, it slows down. And the amount that it slows down is different depending on the frequency of the light. Higher frequency lights like purple, violet and blue will bend more and refract more, whereas red light will refract less because it's at a lower frequency. And therefore, what was just this huge mishmash of all these different colors and therefore indistinguishable, we just saw white light, all those different colors get spread out, and we see this beautiful rainbow with all those individual colors. And it's beautiful, and it's science. And yay. All right. So we see light do that. That points to light being a wave. Another thing that we see light do that points to it being a wave is the fact that it diffracts and interferes. So to really see this, we're going to jump back over to another simulation, courtesy of our friends at the University of Colorado. Thank you, PhET program. All right, so as a reminder, diffraction is this tendency of waves to be able to bend around obstacles and ultimately spread out in that process as they bend around various barriers. And then interference is the ability of waves to overlap each other and to either constructively add or destructively subtract from each other. So we're going to see how light does this in this simulation. So on the left side here, we have a light generator that's just going to start propagating light outward, and we'll see these wave fronts moving along from left to right. And then in the middle of the screen here, we see that they hit a barrier. All right, but there are two narrow openings, these two little apertures in that barrier. And so the first thing that we're going to see is the light diffracting and spreading out and bending around those barriers. And then the other thing that we're going to see is that those two lights then, as they spread out, are going to interfere with each other. So I'm going to stop talking for a moment and let you actually see it. All right. So we see that the light is just moving along from left to right in these nice, happy, straightforward parallel wave fronts here. And then the first thing we see is that diffraction. So our waves spread out as they move through the apertures there. And then because of that, as they spread out, they start to be able to interfere with each other, because they're no longer just all perfectly parallel to one another. We now have these sort of semicircular wave fronts that are now able to overlap. And because they're now interfering and overlapping, sometimes those waves constructively interfere and sometimes they destructively interfere. And so we see then on the far right a screen that's showing us the light that is making it over to the other side. And we see something really interesting here. We might expect that what the light would do as it moves from left to right here and hits the screen is that it would all just sort of be this big blob of light, right? Just light, like you're shining a flashlight on. Or maybe it's like you're shining two flashlights on the screen because you've got these two openings. But that's not what happens. What we see is this very characteristic alternating pattern of light and dark, places where our two light waves are canceling each other out, and places where our two light waves are adding together and getting even brighter. And so this definitely, again, points to a wave model of light, because we're seeing this ability of these light waves to cancel each other out or to add together and get even brighter. This ability of light to interfere and overlap. All right, and so that's what's happening in this image on the right here. We see this this diffraction interference pattern from a couple slits that light is passing through and interfering. Cool. So that also points to this idea that light is a wave. Another piece of evidence in support of this wave model is that Doppler effect. So as a reminder, the Doppler effect basically states that the perceived frequency of a wave is going to be dependent on whether the wave source is moving towards us or away from us. So if the wave source is moving away from us, that's going to stretch out that wave and we're going to perceive a lower frequency. If the wave source is moving towards us, it's going to essentially like scrunch and compress that wave and cause us to perceive a higher frequency. Now, previously we talked about this in the context of sound and how sounds sound lower pitched when the source is moving, it's going to sound lower pitched when it is moving away from you, higher pitched when it's moving towards you. But it turns out the same phenomenon is true for light as well, that if the source of light is moving away from you, the light's going to appear lower frequency or shifted more to the lower frequency end of the visible spectrum. And if a light source is moving towards you, it's going to appear higher frequency or shift more towards the blue or violet side of the visible spectrum. Now, random fun fact for you, I actually made use of this phenomenon to measure and determine the rotational speed of the sun. Because it turns out the sun also spins on its axis just the same way that Earth does. And so as a result, if we think about the sun spinning, that means part of the sun, half the sun, is spinning towards us, and so its light is going to be blue shifted, and half of the sun is rotating away from us, which means that its light is going to be red shifted. So when I was in college, I went and measured the frequency across the diameter of the sun to see how much of a change in frequency we were seeing, how much it was blue shifted on one side, how much it was red shifted on the other side, and then from that I could determine how fast the sun was spinning on its axis. So fun, yay, Doppler effect, and more evidence to point to this wave model of light. So we might say like, oh, that's good, awesome, light's a wave, check, done. But it turns out that's not the end of the story, because there are other things that light does that cannot be explained by this wave model, places where the wave model breaks down, and we have to think of light not as this continuous gradual flow of energy, but instead individual objects, these little packets of energy instead. And so this brings us to a different model, a different way to conceptualize what light is, and we call this the particle model. Right. Now, in the particle model of light, light, again, it's not this gradual continuous wave of energy. Light instead comes in these individual discrete packets called photons, right? And so then the brightness of light is just a function of how many photons we have carrying energy over. And then the color or type of radiation that we're getting is a function of what type of photons we have and how much energy each photon has. So to unpack this model a little bit more, in our table here in the upper left, we see these photons that are making up a bright light. All right, so we see these individual packets of light. It's no longer one big continuous wave. It's 4 little pieces of light. Now, if this represents a bright light, how might we represent, under this particle model, a dim light? So brightness and dimness are just a function of how many photons we have. So if 4 photons is our bright light, then our dim light is just 2 of those photons, all right? So the light appears dimmer because there's fewer photons. There's not as many packets of light coming towards us, all right? Now, if, again, we've got these sort of 4 photons here and they represent a red light, how might we represent a blue light of equal brightness? So if it's equal brightness, that means we still have the same number of photons. So we still have our 4 photons here. But those photons look different. They're a different type, a different flavor of photon than we saw for the red light. So maybe we would represent them this way, that we still have 4 photons, but now instead of being these you know, sort of more spread out photons, instead they're these like squishy photons. So when we're talking about different colors of light, we're talking about fundamentally those packets look a little bit different from each other. And that ends up mattering a lot, as it turns out. So then the different colors that we see and the different types of radiation really just indicate that our photons have different amounts of energy. And it turns out that the energy of a photon is a function solely of its frequency. And so this brings us to our photon energy equation here, that the energy of a photon is equal to the frequency times this constant, Planck's constant, which is always the same no matter what. It's just given the same for every single situation here. And Planck's constant then is always equal to 6.626 times 10 to the negative 34 joule seconds, right? And so that's how we can calculate then the amount of energy that a photon of light has based on its frequency. So just to make sure that we're kind of good on that, here we have a diagram showing us the electromagnetic spectrum here. Based on this, which is going to have more energy, a microwave photon or a photon of visible light? So again, the energy of a photon is a function of its frequency. Energy is linearly related to the frequency of our light then. And if we look at this, visible light is a higher frequency than microwave radiation, which means individual photons of visible light have more energy per photon than microwave radiation does. And that tends to surprise people. People think that microwaves should have a lot of energy because they cook your food. Like wow, that's a lot of energy. And that's kind of true. But the thing is, each individual photon of microwave radiation has less energy than an individual photon coming from your lamp. Okay, the reason that microwaves end up being so effective in cooking our food is because they're at the exact right frequency to excite the water molecules in your food, and that causes your food to get hotter and cooks it and does all that. So like, please do not go sticking yourself in a microwave. I'm not saying that because it's lower energy, it's safe, but just that it objectively has less energy than visible light does per photon. Cute. All right. So now that we've got that kind of squared away here, let's get into the evidence that points to this particle model of light. Now, to understand the first piece of evidence, you have to be familiar with a phenomenon known as the photoelectric effect. Photo meaning light, electric meaning related to electrons, all right? And the photoelectric effect is the science behind solar panels, okay? It's this ability that if we shine light on a material, most frequently a metal, that the energy from that light will generate an electric current because that energy is used to dislodge our electrons, free them from their nuclei, and allow them to go moving along as an electric current. All right. Now, the reason that the photoelectric effect points to a particle model of light is that it only works for certain frequencies. And if you get too low of a frequency for your radiation, it absolutely will not generate a current no matter how much light you have. All right. So, so here we see a graph showing us the energy of our electrons being released for light that is shining on zinc. All right. And so what we see here, this x-axis represents the frequency of light. You can hit zinc all day long with visible light, like just bombard it with like blinding amounts of visible light. The zinc's not going to do anything. It's not interested. But if you start hitting it with a little bit of ultraviolet light, suddenly you're going to end up with a current. Even if the amplitude, the amount of that ultraviolet light is lower than the amount of visible light you tried using, doesn't matter. It's only going to respond to the ultraviolet and higher frequencies. Now, the reason this points to a particle model of light is that if light were just a gradual, continuous flow of energy in the form of a wave, then we should be able to dislodge electrons even with a lower frequency, because all we have to do is just kind of keep shining light on it, or increase the brightness, or just wait long enough until eventually we build up enough energy in our material to get our electrons to be free. But that's not what happens. It turns out that what matters is not the total amount of energy that's being transferred to the object. It's the amount of energy of each individual photon. It turns out that each photon then is responsible for exciting a single electron. And if that photon has enough energy to excite that electron and get it to release and move off as a current, then we see this photoelectric effect. But if each individual photon doesn't have enough energy to excite and release the one electron, it doesn't matter how many photons you're bombarding that material with and how many electrons are getting excited. If the photon doesn't have enough energy to get the electron to be freed, we're not going to get an electric current generated. Okay, so this really points to that particle model, because what matters is each individual packet of light energy, and if that packet has enough to get the electron to be freed. Okay, so energy here isn't just a gradual, slow buildup. It's individual pieces, and we're looking for the energy of those individual pieces there. All right, I hope that kind of makes sense. This is a complex phenomenon, but hopefully that kind of gives you some evidence for this particle model. It turns out that we are not limited to metals and solar panels and stuff like that with this frequency dependence of these behaviors. Turns out that we also are sensitive to the radiation on this electromagnetic spectrum differently depending upon its frequency. So you may have heard of gamma rays, X-rays, and far UV light as being referred to as ionizing radiation. Now, as a reminder, an ion is an atom that has either gained or lost electrons. And so ionizing radiation does just that. It's radiation that has enough energy to ionize atoms, most specifically in you. All right. And so the reason then that X-rays can be so dangerous, that that high frequency UV light can be so dangerous, is it has the ability to drastically alter the atoms in your body, which can cause changes to your DNA, causes mutations, causes cancer. But that again is only relevant at this higher frequency range here. So you can get bombarded with radio waves all day long, and in fact you do. And it's not going to cause cancer. Like it's fine. It's not doing anything to you. Whereas even a teeny amount of gamma radiation is not going to go very well for you. Okay, so same idea here. It's not about the total amount of energy. It's about the amount of energy per packet of light. All right, so this is more evidence for this particle model saying that the frequency matters a lot in determining the effects of light. Okay, so then the big question is light a wave or is it a particle? Those are two different things. And the scientific community says it's both, which is weird to think about and seems like that shouldn't work. But to the best of our knowledge, that's kind of where we are right now. We're sort of like, it's both. And that's it. And over time, we're actually finding that other particles aside from light also exhibit certain wave-like behaviors, but that's a topic for another day and potentially another class. So light is this big, weird, mysterious thing. It's a wave, it's a particle, it's both. So yeah, I hope I blew your mind just a little bit today. That would be great. All right. Anyway, that is all I have for you at this point on waves. Go forth, take good care of yourselves, be safe, and I will see you again soon.